Okay, so today, Caleb, we're going to talk about chemical bonding, chemical bonds, and Lewis structures. I'm going to cover some of the basics with you. So we already know about chemical compounds. We've been learning how to write the formulas for thousands of different compounds, as you know. And you've written your quiz. We can we can write formulas. You can determine the compositions of the compounds as well. We can write balanced chemical equations and use stoichiometry to do chemical calculations. Now, we can do all this without understanding about the atomic structure of the materials that we're dealing with. So the molecular shapes and other properties of the chemicals we're going to study in the next 4 lectures. So we're going to talk a little bit about shapes today. And of course, a lot of substances don't exist as molecules, but they exist as arrays of particles that are joined together by various chemical bonds. So now there are forces involved in holding particles together in crystals, and there are different types of crystals. One type of crystal, they're called ionic crystals that are made up of oppositely charged ions, usually a metal and a non-metal. So other crystals are molecular crystals, like water in ice is made up of actual molecules. Now, within those molecules are covalent bonds, but there are 2 different types of forces. There are forces inside the molecules, and there are forces between the molecules. So, for instance, if we have molecular crystals of chlorine, then there'd be forces between the chlorine molecules, and then there'd be forces inside the chlorine molecules. There are covalent bonds between the actual chlorine atoms in the molecules, and then there are forces of attraction between the chlorine molecules themselves. Now, the intermolecular forces are the ones inside the molecule. They're much stronger than the forces between the molecules, which are called intramolecular forces. So the intramolecular forces, are the forces inside the molecules, and the intermolecular forces are the forces between the molecules. Now, the interactions that hold these particles together, and the particles can be either ions or molecules or atoms, we collectively call them chemical bonds. There's different kinds and different models to enable us to understand them. Now, to assist us in understanding chemical bonds, we like to use various terms. A gentleman named Gilbert Lewis, he certainly noted that the noble gases, which are group 18 in the periodic table found on the far right, don't interact with other elements easily. They're inert for that reason. And why they were inert, it was decided it's because they have electron configurations where they have a completed group of 8 electrons around the atoms. We call that a completed octet, and we refer to that as the octet rule in chemistry. So greater stability is achieved when atoms can actually achieve an octet, either by losing electrons or gaining electrons or sharing electrons. So the atoms combine to achieve more stable electron configurations, like are found in these noble gases on the far right of the periodic table. So just to bring that to light, I'm talking about these elements here: helium, neon, argon, krypton, xenon, and radon. All have completed octets, or 8 electrons around the outer shell. So the maximum stability results when an atom is isoelectronic with a noble gas. And isoelectronic simply means has the same number of electrons as. So the electrons of prime importance are those found in the outermost shell. We call that the valence shell. And it's these electrons found in the outermost shell of atoms that are involved in these chemical bonds. Now, the core electrons are the electrons found in energy levels that are closer to the nucleus. Typically, they're not involved in the chemical bonding, but in rare occasions, they can become involved. So a Lewis dot symbol really represents the electrons in the outermost shell, and those are the electrons that are involved in the bonding. And we like to draw diagrams showing how many electrons are involved in bonding for a particular atom, so we can understand how those atoms combine with other atoms when they form chemical compounds and the bonds involved. Lithium, for example, the number at the top here, 7, is the nucleon number. That tells us the number of protons and neutrons. And the number at the bottom is it's the atomic number. It tells us the number of protons. And of course, in a neutral atom, if we have a charge, we're going to put the charge in the top right. In a neutral atom, the number of protons and the number of electrons are equal. So we can also refer to the atomic number with the letter Z and the nucleon number or mass number with the letter A. And lithium, like I said, will have 3 protons in its nucleus. If it's neutral, it'll have 3 electrons in its in the shells outside the atom. So there's a terminology I'm going to use to describe atoms. And if we can visualize it this way, we can see this particular isotope of lithium, because its mass number or nucleon number is 7, it has 4 neutrons, it has 3 protons. The neutrons aren't involved in bonding, so we really won't consider them today. And since there's 3 electrons, there's 2 electrons in the first energy level in the s orbitals. There's a 1s orbital, so those 2 electrons would be in the 1s orbital. And then in the second energy level, there's s orbitals and p orbitals, and there's 1 electron in this case in the 2s orbital. And that's how I could, again, show it in another diagram like this. So the atomic core are the electrons inside in that first energy level. They're not involved in bonding. Only the valence shell electrons are involved in bonding. In this case, lithium has 1 valence shell electron that's involved in bonding. And typically we can figure out the number of valence shell electrons from the group number it's in. Again, looking at the periodic table. Valence is one of those odd words in chemistry that has multiple meanings, and I'm going to use it in a couple of different contexts. For now, we're going to say the number of electrons in the outer shell of atoms in this particular chemical family are 1. This chemical family is 2. Most transition metals have 2. This family, boron, aluminum, have 3. Carbon family, 4. Nitrogen family, 5. Oxygen family, 6. Fluorine family, 7. And the noble gases, 8 valence shell electrons. So again, we can see that from this periodic table. I went to the bigger periodic table. Same thing is showing in the smaller one here. So a Lewis structure, let's talk about what it looks like. So we write the symbol of the atom, lithium, and we talk about the valence shell electrons, the electrons involved in bonding. Lithium has 1 valence shell electron, so we show a single electron, and it can be placed in any of the 4 positions around that symbol. So we've already done the lithium atom. Now let's talk about ions, like a fluoride ion. Okay, so now the maximum number of electrons in each energy level can be determined by using the formula 2n squared. So if the energy level was 2, in the second energy level, 2 squared is 4, times 2 is 8. You can have 8 electrons maximum in the second energy level. In the third energy level, n would be 3. 3 squared is 9, times 2 is there's 18 possible electrons available in that third energy level. So lithium has 1 valence shell electron. A fluoride ion, typically when we draw diagrams of Lewis structures of ions, we put them in brackets. And here we're showing the fluorine is a halogen. It's in this group here, group 17, has 7 valence shell electrons. You can see there in red. But since it ends in IDE, it means it gained an electron in this case because it's a non-metal. It becomes isoelectronic with the nearest noble gas. To do that, it gains a single electron. That nearest noble gas is neon, which is right beside the fluorine atom in the periodic table. So we can show it as an additional electron. You don't necessarily need to show it with a different symbol. You could use the same symbols, and we put the charge outside the bracket. Now, a calcium atom has 2 electrons in its outer shell. So we can show the electrons here. I'm putting them on opposite sides because electrons repel each other. They're both negatively charged, so they tend to get as far away from each other as possible. This would be the calcium atom's Lewis structure. Now, if it's an ion, we would simply show it with brackets around it, and these 2 electrons would be lost. As calcium becomes more stable, it loses its valence shell electrons and achieves the electron configuration of argon, which is the nearest noble gas. It's isoelectronic with argon, meaning it has the same number of electrons as an argon atom. And we show the charge again outside. Now, negative ions are called anions. So just another name, terminology. Now, a simple table of valences. You can see here how we have the group numbers. I'm using the old group numbers that are on the old periodic tables. The new group numbers go from 1 to 18. I hope that doesn't confuse you. But we can see the Lewis structures we most frequently use are at the bottom here. Group 1 of 1, group 2, 2, 3, 4, group 5. Notice that we start pairing them up. 6, 7, and 8 are the more common ones. The ground state simply refers to the atom before some of the electrons are promoted to enable bonding. So I'll most often refer to the normal valence state because that's the structure of the electrons when they form chemical bonds. So valence can be used to refer to the number of electrons normally involved in bonding. So in this case, lithium valence is 1, beryllium is 2, boron is 3, carbon is 4. Nitrogen, because these 2 electrons are paired up, we say its valence is 3 because it normally forms 3 chemical bonds. Oxygen, we have 6 electrons, but 2 of the electrons are, 4 of the electrons are in 2 pairs that are paired up. So we can say the valence of oxygen is 2 because it normally forms 2 chemical bonds. Fluorine has 7 electrons in its outer shell, and it pairs up 3 of them, and we have a single electron available for bonding. And something like neon has a valence of 0 because there are no electrons available for bonding under normal circumstances. So now if we identify the actual location of the electrons, beryllium is, it has 2 electrons in the first energy level in the 1s orbital, and it has 2 electrons in the s orbital, the second energy level's s orbital. So we can say it's 1s2, 2s2, and I'm only talking about the valence electrons, so I just show the 2s2. Now, boron has 2 electrons in the 2s and 1 in the 2p. So that would be the 2p, and those are the 2s electrons. Carbon has 2s2, and then we have 1 in the px and 1 in the py. Again, there'd be a px, a py. And nitrogen, here's the electron arrangement. It's 1s2, 2s2, 2p3, px1, pxy, py1, pz1. Now, normally when these particular materials, these elements form bonds, they hybridize their orbitals together. The s and the p orbitals will hybridize into one type of orbital that all have the same energy levels, same amount of energy. So we call them sp hybrids. If there's 3 p orbitals that hybridize with an s, we call it an sp3 hybrid orbital. So in the case, we can hybridize this s orbital in the second energy level with a p orbital, and we get an sp hybrid. So we get 2 sp hybrid orbitals for beryllium. For boron, we can hybridize 2 of the p orbitals and 1 s orbital. So we get, in the second energy level, we can get 3 sp2 hybrid orbitals that all have the same amount of energy in boron. In carbon, we can merge 3 of the p orbitals with an s orbital, in the second energy level, and we get 4 equivalent orbitals that are hybridized into 4 sp3 hybridized orbitals for carbon. All of these hybrid orbitals have equal energies. Now, oxygen, as we noted earlier, has a valence of 2, meaning it tends to form 2 chemical bonds. And if we have a molecule of water, we can see that oxygen bonds with 2 hydrogens. And if I was going to show Lewis structures, the electrons of hydrogen shown with the little x's. When it bonds with the oxygen, I can see that there are 2 electrons available for bonding. These pairs of electrons are already stable because they're paired up. And we can show it, instead of putting symbols like x's or circles, zeros, little dots, we can use sticks to represent chemical bonds, which you've seen repeatedly in textbooks. I can show unbonded pairs of electrons with sticks like this as well. So it doesn't matter to me which types of symbols you use. I want you to understand they mean the same thing. And we can use designations where we can use A as the central atom. In this case, it's oxygen. X refers to the atoms that are bonded to the central atom, in this case, hydrogen. And E represents the number of unshared pairs of electrons. In this case, there's 2 unshared pairs of electrons. That would be represented by E. So this particular molecule would be represented by A, X2, E2. A, the central atom being oxygen again, X, the atoms it's bonded to, and E are the unshared pairs of electrons. And I can use a number that's called, I can say there are 4 pairs of electrons around the central atom, or there are 2 atoms bonded to it, and there's 2 unshared pairs of electrons. And if I wanted to visualize this particular molecule, I use a program frequently. If you go to any search engine and type in PHET for the University of Colorado, you'll get these simulations, which are just wonderful to use. I love using them. You can play around with them. This one's called Molecular Shapes. You'll see there's a whole bunch of them for physics and chemistry and math. You'll find them useful for many courses to visualize. So this would represent kind of like the model for a water molecule. The 2 unshared pairs of electrons influence the shape. If I took those 2 unshared pairs of electrons away, we would simply have a linear shaped molecule. These unshared pairs of electrons have a repulsive force that we'll talk about later in another lecture, but it influences the shape. So a water molecule is actually angular or bent. So its angle between the atoms is 104.5 degrees, and that's a typical water molecule. So I'll go back to my lecture now. Whoops, sorry. Here we are. Now, nitrogen has a valence of 3 because one of the pairs of electrons, one of the groups of electrons, 2 of them are paired up in that valence shell. So we have 3 single electrons that are easily bonded. So we can combine them typically with 3 hydrogen atoms. Hydrogen has 1 valence shell electrons to form a molecule of ammonia, a very pungent, strong smelling gas. And again, if I was to use the same terminology, the central atom nitrogen is joined to 3 atoms. E is the number of unshared pairs. So I use a 3-number code, 431. 4 means there's 4 pairs of electrons around the center atom. 3 means there's 3 atoms bonded to the central atom, 3 hydrogens. And 1 tells us there's 1 unused pair. And again, if I wanted to visualize what this molecule looks like, I can use this particular model here to demonstrate to you what it looks like. You can see that that unshared pair of electrons affects the shape again through repulsion. We call this a pyramidal shape or a trigonal pyramidal shape. There's 3 atoms, unshared pair. If I didn't have an unshared pair, it would simply be trigonal planar. They'd all be in the same plane. But this unshared pair of electrons repulses the other electron clouds that are representing the bonds formed between the nitrogen and the hydrogen atoms. And the shape of that molecule is a pyramid. Now, the ground state of some of the elements are not the same as their normal valence state. So electrons are not necessarily configured, as I said earlier, the same in an isolated atom as they are when the atoms form chemical bonds. And that's because the sp and p orbitals will hybridize to create equivalent energy levels so that you can form equivalent bonds between atoms, like in ammonia here. We have hybrid orbitals. Now, we can split sometimes the pairs of electrons that are the unpaired electrons that aren't being bonded. We can split them into individual electrons sometimes to create equivalent bonds. Now, in the case of beryllium, the 2s electron pair is split into two unpaired electrons, and they're not normally called s or p orbitals. They're called sp hybrid orbitals in a beryllium atom. In the case of boron, and carbon, the lone pairs are split into single electrons. In each of these cases, the valence is increased by 2 for each lone pair split up. Again, valence means the electrons that are involved in the bonding. This is possible in the second shell, where n equals 2. There's a total of 8 electrons, and there could be 4 orbitals in which the electrons can be put to minimize the expense energy-wise. So we talked about how in carbon we have sp3 hybrid orbitals. We can form 4 different equivalent hybridized orbitals to form 4 equivalent bonds. Now, sometimes when a carbon atom is involved in bonding, the following occurs, like we've just talked about. So this carbon atom can bond with 4 hydrogens in a molecule of methane. The gas that we emit from our bodies after we eat certain foods, we tend to produce quite a bit of this gas. It is flammable, so you have to be careful. But we can describe the orbitals as sp3 hybrid orbitals, and 4 hydrogen atoms can bond with carbon, and you can get a shape of a molecule, and I'll show you what the shape would look like here. There's what it would look like. Note that the bond angle's there, 109.5 degrees between each of these equivalent bonds. So the only way to explain that these bonds are equivalent is to develop a model that hybridizes the sp orbitals. When we experimentally look with X-rays at the structure of these particular molecules, we discover that the bonds are all equivalent in energy, and they have this particular geometry. This has been verified experimentally. So we can show the electron pairs, that, and the X's simply are represented, can be designated that they come from a different atom. The carbon atoms could be visualized here with the red dots, and the hydrogen atoms, electrons, with the X's. Now, the lone pair of electrons in nitrogen can be split as well under unusual circumstances, but most of the time it is not split because in the second shell, there aren't enough orbitals to accommodate 5 single electrons. So it's very unusual to see nitrogen forming 5 bonds. It can happen, but it's unusual. So that's why the typical structure when nitrogen bonds with hydrogen is NH3. There is no NH5 that is observed. So this pair of electrons tends to stay together in this case because nitrogen only has 2 energy levels. It can only put 8 electrons in that second energy level. We can't put 10. So we couldn't form 5 equivalent bonds with 5 hydrogens with 10 electrons. There'd be too much repulsion of those 10 electrons in that second energy level. So typically nitrogen, it has, in this case, it has 2 electrons in the 1s orbital, 2 in the 2s orbital, and then 3 in the 2p orbitals, 2px, py, pz at different orientations. So the core electrons would be in the first energy level, those two, and these 5 electrons are what are involved in the chemical bonding. And like we said, typically 2 of those 5 electrons are paired up. So ionic bonds we'll talk about now typically occur between a metal and a non-metal. They're bonds where one atom loses electrons, another atom gains an electron or electrons, and that's because they achieve a more stable arrangement when that happens. They acquire electron arrangements of the nearest noble gases, and each, by losing electrons and by gaining electrons, they can attain an octet rule, which means they have 8 electrons in the outermost energy level. So the group 1 and 2 metals frequently bond with group 16 and 17 nonmetals. So in an ionic bond formation, the metal typically loses electrons and the non-metal gains electrons. And they do this to become isoelectronic with the nearest noble gas, as we talked about earlier. We form anions and cations, oppositely charged ions that are basically held together by this attractive force between positive ions and negative ions. And we call that type of interaction a Coulombic interaction. So a simple example here is sodium. A sodium atom has 1 valence shell electron. A chlorine atom has 7 valence shell electrons. It's easy for sodium to simply lose its 1 valence shell electron to the chlorine atom. And when we show it as sodium chloride, we can see that the sodium has lost its 1 valence shell electron, become isoelectronic with the nearest noble gas, which was neon. And the chlorine, again, achieves its stability by gaining an electron and forming the same electron arrangement as the nearest noble gas, argon. So because they're oppositely charged ions, they are attracted to each other. So the reason why they have charges is because, remember, sodium atoms start out with 11 protons and 11 electrons, electrically neutral. The electrons, the 11 electrons, 2 in the first energy level, 8 in the second, 1 in the third. Chlorine has 17 protons and 17 electrons when it's neutral. It has an arrangement of 2, 8, 7. 2 in the first energy level, 8 in the second, 7 in the third. When they combine, again, as we've said, the sodium loses its electron, the chlorine gains an electron, so the sodium atom becomes a sodium ion, which has a charge of positive 1. Chlorine becomes a negative ion, its charge becomes a negative 1. So a term we can use, a positive ion, can be called a cation. And in a cation, you can see that the T kind of looks like a positive sign. In the word anion, the second letter is N, stands for negative, I guess, a negative ion. So it's just a simple way of trying to remember the difference between a cation, which is a positive ion, and an anion. In this case, the sodium's the cation, the chloride is an anion. And typically the name of an anion ends in IDE, chloride ion, as opposed to a sodium ion. We don't change the ending of the cation's name. So the core electrons would be the 2 and 8. And similarly, in the chloride ion, the core electrons would be the first 10, 2 and 8. They both now have achieved stable octets by losing and gaining electrons. And they're held together by this electrostatic force of attraction, a Coulombic attraction. Now, here's another example for magnesium oxide. Again, magnesium has a valence of 2. It's got 2 valence shell electrons. Oxide has 6 electrons in its outer shell. Again, if magnesium loses 2 electrons to oxygen, which gains the electrons, we can get a stable arrangement. Each of them becomes isoelectronic with a noble gas after it becomes an ion. So we have a magnesium ion and we have an oxide ion. And again, if we do the accounting for the protons and electrons, we can see to start with how many protons and electrons there are. We can see the magnesium loses 2 of its electrons to become more stable. Those electrons are not very tightly held. Oxygen has a much stronger pull on electrons than magnesium does, so it tends to steal the electrons, and we form an ionic bond with 1 ion of magnesium and 1 ion of oxygen. In general, metals have lower ionization energies and form cations. An ionization energy is the amount of energy it takes to remove an electron from an atom. So magnesium only has 2 electrons. Those electrons are fairly far from the nucleus, so they're easily removed. As we add protons to an atom's nucleus and the same number of energy levels, the energy levels get pulled closer, so the electrons are harder to remove because they're closer to the nucleus. So atoms like oxygen have a fairly strong pull on electrons for that reason, because oxygen atoms only have 2 shells of electrons, but 8 protons pulling on them. And nonmetals tend to have higher ionization energies for the reasons I've said. The electrons tend to get pulled closer to the nucleus as you move across the periodic table. You've got the same number of energy levels, but more protons in the nucleus that are pulling on the electrons. So nonmetals tend to form anions or negative ions, and metals tend to form cations or positive ions because they lose electrons and nonmetals gain electrons. So now let's talk about the sharing arrangements that can happen in covalent bonds. We don't get losses or gains of electrons, but we get sharing of electrons to achieve greater stability. So when similar atoms, usually 2 nonmetals, bond together, electron transfer doesn't occur, but electrons are shared. So in this case, we can see hydrogen can form a more stable arrangement. Remember, the noble gas helium only has 2 electrons, so that we can fill that first energy level by having 2 electrons. So each hydrogen atom, if we look around it, has 2 electrons, so it's more stable. We can shore the bond with a stick. Chlorine, on the other hand, chlorine atoms have 3 shells of electrons. They can achieve more stability. If we just show these 7 electrons that are involved in bonding in the outermost energy levels, we can see that when we draw a circle around each chlorine atom, there are 8 electrons. And each chlorine atom now achieves greater stability by sharing an electron pair. So we can see that there's lone pairs of electrons as well. And there's a bonding electron pair, an electron pair that's being shared by each chlorine atoms. So we do like to show lone pairs sometimes. We don't always show them. Sometimes we simply show it without those symbols. So if we show the bonding that occurs, a covalent bonding between phosphorus and chlorine, which are both nonmetals, they both have fairly strong pulls on electrons. So when they form greater stability, we can have 3 chlorine atoms bonding with 1 phosphorus atom. And instead of using dots, I can use sticks to show the bonded pairs. And in this case, I'm not showing, we know there's 6 electrons total that are around each chlorine atom that are not being shown in this diagram. We sometimes show them and sometimes we don't. Depends on the context. So we can see that phosphorus, in this case, forms 3 stable bonds, and we have a pair of electrons, again, that's not bonded. So 3 pairs of bonding electrons, 1 pair of non-bonding electrons. So the normal valence of phosphorus is 3 because of that 1 pair of electrons. These 3 electrons are involved in bonding or sharing relationships with other atoms, in this case, chlorine. Now, chlorine tends to form one bond because of the 7 electrons arranged. 6 of the electrons are placed in pairs. Now we can use dashes for electron pairs. Instead of drawing, this diagram takes quite a bit of time to draw, so it's easier to just use sticks to represent the shared electron pairs. This is called carbon tetrachloride. And we don't always show, again, like I said, it's implied there's 3 pairs of unshared electrons around each chlorine atom here. We're not showing them. So we simply use sticks to represent those particular bonds. And now we have ammonia. We can see again, there's 3 bonds formed between nitrogen and hydrogen, shared electron pairs. And we can also represent it, and we can leave out that electron pair. Now, if we're considering shape, of course, that electron pair does influence shape. So it's important when we talk about shapes. But if we're just talking about the formula of ammonia, we can use this diagram. If we're talking about the shape, it's better to indicate that there is a pair of electrons here that's involved in determining the shape of this molecule, which we'll talk in more detail in the next lecture. Now, there are also multiple bonds that are formed between 2 atoms, where you get double bonds or triple bonds. So for instance, in ethene, C2H4, we end up with 4 electrons or 2 pairs of electrons being shared between adjacent carbon atoms. And in this example, we have carbon monoxide. The reason why there's a triple bond formed is if I was to look around this oxygen atom, it has 8 electrons surrounding it. So it's more stable with, again, that octet arrangement. And this carbon atom has 8 electrons as well. It's more stable. So that's why the carbon forms triple bonds with oxygen to achieve greater stability. If we don't form a triple bond, we don't get the stability in carbon monoxide. So we get a triple bond here. Now, the number of bonds between 2 atoms, we typically call the bond order. In this case, the bond order is 3 between carbon and oxygen here for a triple bond. Now, the normal valence of carbon is 4, and the normal valence of oxygen is 2. And the only way we can connect these 2 together, again, is to use double bonds. If I look at a circle here showing there's 8 electrons around oxygen, there's 8 electrons around this oxygen, and there's 8 electrons around the carbon. By establishing 2 double bonds, we can create stability in carbon dioxide. We say the bond order between these carbon and oxygen atoms is 2. Now for C2H4, we have a bond order of 2 between the 2 carbon atoms, but a bond order of 1 between the carbon and the hydrogen atoms. Now, sometimes I can put those electrons side by side. I can put them one on top of the other. It doesn't really matter. So here's a typical diagram showing the chemical bonds between the carbon atoms and the carbon and hydrogen atoms in a molecule of ethane. Now, these 2 molecules are isoelectronic. What does that mean? It means they have the same number of electrons. Each nitrogen has 5 electrons involved in bonding, so there's a total of 10 electrons. Each carbon has 4 electrons involved in bonding for a total of 8. Each hydrogen has 1 electron involved in bonding for a total of 10. So we can see they each have 10 electrons involved in bonding. That's why they're isoelectronic. So the only way we can form those particular bonds is to create, in this case, C2H2. In order to achieve stability, carbon has to have 8 electrons around it. We need to form a triple bond between the 2 carbons. So now when I look around this carbon atom, it's got 8 electrons. When I look around this carbon atom, I can see it has 8 electrons. And hydrogen, each hydrogen atom has 2 electrons because it only has 1 energy level. The first energy level is stable with 2 electrons, as it is in the noble gas helium. So they all achieve the electron arrangements of noble gases by sharing electrons in this way. So we call this a third order. And again, nitrogen, if we're forming an N2 molecule, we can see, again, we can arrange the electrons. If we look around this nitrogen atom on the left, there's 8 electrons. We look around this nitrogen atom on the right, there's 8 electrons. Each nitrogen atom has achieved greater stability through the accumulation of 8 electrons around it. And again, the bond order is 3 here. Bond order for the carbon and hydrogen is 1. The bond order between the 2 carbons is 3. Now, that's the end of the lecture today. Our suggested homework here is to read your textbook between those 2 pages, 372 to 380. Go over examples 10.2 and 10.3 in chapter 10.